Hello and welcome to the Unit 6 Section 3 video on extraneous solutions and real-world situations. Now, just to remind you, we are in Unit 6, so we are talking about radical equations that have a radical symbol in them, whether it be a square root or a cube root or a fourth or fifth or sixth root. Any type of radical is what we're dealing with in this unit. So let's recall the steps that we talked about in the last section to solve radical equations. Basically, all you're trying to do is isolate the radical, raise both sides of the equation to the power equal to the index of that radical, and then simplify and solve. When an equation contains two radicals with the same index, what you do is raise each side to the power that eliminates the radical. So we have an example here of that. So we're going to solve square root of 35x equals 5 times the square root of x plus 2. What you're going to do is you're going to take each side, raise it to the second power. So we got the square root of 35x raised to the second power. And then you take all of this, 5 times the square root of x plus 2, and you're going to raise that to the second power. So on the left-hand side, you end up with 35x because the square root and the square cancel each other. On this side, we have that 5 out in front. So what you have to do with this 5 is square it. So that gives you 25. And then we're left with what's in the square root. The square root and the square cancel each other, so you have 25 times x plus 2. So from here, we're just solving for x. We distribute the 25, so you get 25x plus 50. We subtract 25x from each side, so that gives us 10x equals 50, and so x equals 5. And that's really all there is to it. Now, let's talk about extraneous solutions. Recall that extraneous solutions occurred in rational functions because you cannot divide by 0. Okay, remember, whatever's in the bottom can't be 0 in a rational function. So if we had a value of x that made 0 in the bottom, then we had to throw that value of x out as a solution. Similarly, extraneous solutions can occur in radical functions because you cannot get a real solution when you take an even root of a negative number. So it's very important to note that this is only the case for radicals with an even index, square roots, fourth roots, sixth roots, because you can take the cube root or a fifth root or a seventh root of a negative number. Okay, because the cube root of negative 8 is negative 2. And we talked a little bit about how that works in the last section of notes. So to check for extraneous solutions, plug in the solutions back into the original equations. An extraneous solution results in a false statement. Okay, so let's do an example of this. We're going to solve the square root of x plus 18 equals x minus 2. So as we did before, we're going to square both sides. And when you do that, the square and the square root on the left-hand side are going to cancel. So you get x plus 18 on the left-hand side. On the right-hand side, we're going to expand this binomial to x squared minus 4x plus 4. And now we want to solve for x. So to do that, we're going to get everything on the one side and have 0 on the left-hand side. So you got x squared minus 5x minus 14. And now we're going to factor this so we can solve for our values of x. And it factors down into x plus 2 times x minus 7. And so our values for x are going to be negative 2 and 7. Well, let's check both of these values. Okay, let's start off by checking x equals negative 2. So we're going to plug in negative 2 in for x in our original. So we got negative 2 plus 18. And then over here we've got negative 2 minus 2. Square root of negative 2 plus 18, well, if we take 2 away from 18, we get the square root of 16. On the right-hand side, we have -4. Square root of 16 is 4, and so 4 does not equal -4. So you're going to have to throw out -2 as a solution. Now let's check x equals 7. Like we did with -2, we're going to put in 7 for x. So on the left-hand side, we get the square root of 25. On the right-hand side, we get 5. So 5 equals 5, and this one checks out. So therefore, x equals 7, and only 7. All right, so the second half of this section involves real-world applications. Okay, so we're going to do a few examples of this. For example 3, let's take a look at a music application. Frets are small metal bars positioned across the, and this should say neck, the neck of a guitar, so that the guitar can produce the notes of a specific scale. To find the distance a fret should be placed from the bridge, multiply the length of the string by 2 raised to the -n/12th power, where n is the number of notes higher than the string's root note. If the length of the string is 64 centimeters, where should the fret be placed to produce a G note on the E string, or in other words, 3 notes higher? So, as the problem tells us, we need to multiply the length of the string by this factor. So the length of the string is 64 centimeters. So that's 64, and we're going to multiply it by 2 to the negative, and our n value is the number of notes higher than the string's root note, so that's going to be 3 notes higher in this case. So you got -3/12. Now you could put this in your calculator, but let's do a little simplifying first. 64 times 2 to the -1/4 is what that exponent reduces down to. And then we've got 64. If we want to get rid of the negative exponent, it gives us 64 over 2 to the 1/4. And we find that that's approximately 53.82. So, it's great that we found a value, but remember, as always, we have to put this into context. So we're going to write a word answer to answer this word problem. The fret should be placed about, because this is an approximate answer, 53.82 centimeters from the bridge. And that's really all there is to this problem. Let's move on to example 4. So in this one, we're taking a NASA application for this. Special airbags are used to protect scientific equipment when a rover lands on the surface of Mars. On Earth, the function, given here, approximates an object's downward velocity in feet per second as the object hits the ground after bouncing x feet in height. The corresponding function for Mars is compressed vertically by a factor of about 3/5. Write the corresponding function for Mars and use it to estimate how fast a rover will hit Mars's surface after a bounce of 45 feet in height. So, first thing we need to do is write the function for Mars. So the function for Mars is going to be g of x, and we're talking about a compression, a vertical compression of about 3/5. Well, that's our a value. So that's just going to go out in front of the function that is being compressed. Now we need to find the value for g of 45. Well, for g of 45, we just plug in 45 for x. And when you put that into your calculator, you get approximately 32. And again, we need some context here. So the context is the rover will hit Mars's surface with a downward velocity, and it's okay if you just put velocity, of about 32 feet per second at the end of the bounce. And that completes that problem. All right, let's wrap up this section and this unit with one last word problem, and this one pertains to driving. And this is actually a very real-world type of a problem that's used all the time. So the speed s in miles per hour that a car is traveling when it goes into a skid can be estimated by using the following formula, where f is the coefficient of friction and d is the length of the skid marks in feet. After an accident, skid marks are measured to be 120 feet in length. The driver claims to have been traveling the speed limit of 45 miles per hour. The coefficient of friction under the accident conditions was 0.7. Is the driver telling the truth about his speed? And explain. Okay, so what we're going to do is figure out what the distance of the skid marks would be if he had been traveling at 45 miles per hour and see if that happens to be 120. So his speed was 45, so that's going to go in for s. Then we have the square root of 30 times our coefficient of 0.7 times d. D is what we're trying to find, and we're going to see if that happens to be the same as 120 feet. So, to solve this, first let's multiply 30 and 0.7, so that's going to give us 21d. And then we're going to square both sides, and when we do, we get 45 squared on this side, we get 21d on this side. 45 squared is 2025. And we divide each side by 21, and you get approximately 96. So the skid marks were actually 96 feet in length, not 120. Or would be if you were going 45. But since the skid marks go longer, it means it took him longer to stop, which means he was going faster. So let's put all of this into a sentence to sum this up. If the driver were traveling 45 miles per hour, the skid marks would measure about 96 feet. Because the skid marks actually measure 120 feet, the driver must have been driving faster than 45 miles per hour. So because we had to do some explaining, it took a little bit more to write. But there you go. There's the explanation, and the math backs that up. Now the question may come up, well, how fast was he driving? Well, you can easily find that as well. If you just take 120, put that in for D, you got your F, and you're going to solve for S. So you do the square root of 30 times 0.7 times 120. And if you do that and put in your calculator, you're going to find the driver was going about 50 miles per hour. So he was speeding by about 5 miles per hour over the speed limit. So there's that for your extra information as well. And that is another way that you could go about this problem to see if the driver was telling the truth. Put in the measure of the skid marks to see what his speed was and if it was indeed 45 miles per hour. Okay, so this wraps up this relatively short section of Section 3 of Unit 6, and that wraps up the unit. So as we move forward, Unit 7, we will be discussing exponential functions.